Security and Policy Initiatives.
Hello and good morning to everyone, and welcome to this webinar by the Security and Policy Initiatives, SAPI, a Think Factory. Today is a part 2 of the Demystifying Artificial Intelligence webinar series brought to you by SAPI to declutter certain aspects about the very important and inevitable technology that is artificial intelligence. We will have a talk by Mr. Deep Prasad today on this topic. Before we move on, I would request Mr. Pradeep Gupta, founder of SAPI, to give a brief introduction to the topic. Just to give you some idea, Mr. Pradeep Gupta is a seasoned bureaucrat and technocrat who has served in the government at various levels, ranging all the way from the PS to the Honorable President of India, to working in various ministries such as Defense, Finance, Home, among others. Along with this, he was also a part of OFB, the Ordnance Factory Board, and has a keen interest in new technologies such as artificial intelligence and quantum computing, which is one of the reasons why we've brought this very interesting topic for you today. Without any further ado, I will request Mr. Pradeep Gupta to give a brief introduction on the topic. Thank you.
Good morning, everybody. Thank you, Sarang, for the introduction. At the outset, I welcome Dr. Sithanu Pillai, distinguished scientist from DRDO, father of BrahMos missile, Padma Bhushan, Padma Shri, who has made tremendous contribution to the field of weapon development in this country. Deep Prasad, the keynote speaker of today's session. We have amongst us veteran Colonel D'Souza and other participants, scientists and engineers from various institutions. Friends are also one of them from media. So we will be, I'll be just giving you a small glimpse into what is quantum computing and how it has progressed from the initial stages. It is the penchant of the human mind to understand, explain the things which is around him. And this led to development of classical physics long ago. And as the classical physics has its own constraint of deterministic in nature, it was not able to explain several features, several phenomena. This led to development of quantum mechanics. It was, of course, in theoretical domain, and then we tried to explain the things which are probabilistic in nature, which are unpredictable. The conventional computers, what you see, are operating on the binary bits, and that is on the principles of classical physics. However, the quantum mechanics, which was there earlier, has now found its way in the operations arena and through the quantum computers, which is its own way of functioning and analyzing the information and processing it. So there is a fundamental difference between this classical computer, what we call this laptop, what we are operating right now, and the quantum computers, which operate on the qubits, which has infinite possibilities of its storing and manipulating the information. This is the major point which makes it different to the classical computer, and it has the, at the same time, it can be in different shape and different positions, and different information can be then be manipulated. This is making all the difference with the conventional computer. The quantum computers, because of this enormous computational power, it can even break the most complex encryption codes and the cryptographic codes. However, notwithstanding this particular trait of the quantum computers, its advantages are quite a lot because it performs very fast in the with huge data sets. It has three fundamental characteristics to do: this superposition, entanglement, and interface. And Deep will be explaining all these areas, how it is operating. IBM, for the first time, brought the quantum computer in public domain. It was in 2016, and since then it has never been stopped for this particular field to evolve. And we are telling that everybody that this decade is the quantum computer decade. The software of the quantum computing is designed to target the quantum architecture, and it is known as quantum algo. However, there are limitations to the quantum computer, but notwithstanding, it holds big promise. Now, coming to the AI, AI, as you know, counts on processing large and complex data sets. It learns, infers, and understands the data set till it stops making error. But if there is a data set which is huge, it takes time, and it's not possible to have real time. Here, the quantum computer will make a lot of difference, and like in NLP, if you are processing, it will be the real-time interaction with the voice and the understanding of the computer. The quantum computer, because of this enormous computational power, it holds big promise, and I say that the quantum computer is a force multiplier to the AI, while AI is the force multiplier for the conventional laptop for computers, what we have just now. And SAPI has chosen this very field because we feel that it holds the key for us to, the Indians, to leapfrog the technological race, what we have missed out in the past. And it is a very good way if we adopt at least in the design and the other stages we can do. The potential use cases of the quantum computing are to the discovery of the newer material, the design of the newer material, or the control systems, the supply chain, and there are so many other areas where it can be applied. Because semiconductor evolution and the semiconductor research with the materials, if we say what Deep will be describing, takes enormous amount of time, money, capital, everything if we use the conventional way. Here, he will share his ideas that how we can leverage the AI and the quantum computer to come up with a better design of the material, which will have better computing power. And we may get to patent few of these in India if I do it, and then the manufacture can be taken up accordingly, either in India or elsewhere, but then we hold the key to that material. So this is the whole idea with which we are organizing this webinar of today. So it is in this session of today, we have just got some brief idea. And the overall session will give you a glimpse that how QC and AI enable a roadmap for the entities with appropriate technical expertise to work on a simulation first approach over next 5 to 10 years. Deep Prasad will share his brilliant ideas here, and he will be telling his idea that how to practically do the thing. Thank you.
Thank you very much, sir, for a very apt introduction on the topic and the relevance and importance of quantum computing, artificial intelligence, and the overall semiconductor industry. We will now move on to the talk by Mr. Deep Prasad. Before we get started, I would like to give a brief introduction on Mr. Deep Prasad. Deep is a graduate in industrial engineering from the University of Toronto, Canada, where he worked on various topics and researched various topics such as artificial intelligence, blockchain, and quantum computing. After graduating from the University of Toronto, he worked with the Royal Bank of Canada on usage of artificial intelligence in the banking sector, after which he worked on usage of blockchain technology in the healthcare sector, and finally started working and developing his technology in quantum computing particularly in the domain of material sciences, through a company that he founded called Quantum Generative Materials, also known as GenMat. Just to give you a brief idea about GenMat has recently raised $50 million as a very high valued startup. GenMat is one of the very first companies in the entire world to be leveraging the use of quantum computing technology, especially with the help of artificial intelligence in the simulation first approach, as Pradeep sir mentioned. They are working on using this technology to develop various new materials, which are very expensive and complicated to design. Apart from just designing new materials, they're also working on quantum sensing technologies. And something that has been made non-confidential very recently is a very interesting project that GenMat is working on, which is to launch a quantum sensing satellite into space for observing the Earth, particularly in the domains of mining. Without any further ado, I will request Mr. Deep Prasad to start his talk. Over to you, Deep. Thank you.
Awesome. Thank you, Sarang. Really appreciate the introductions from both you and Pradeep, sir. I'm just going to share my screen. Let me know when you can see it. Okay, great. So, yeah, hi, everyone. My name is Deep Prasad. I appreciate everyone taking out some time out today and just learning a little bit about what I wanted to share. And as we've discussed in the abstract of this, this meeting, the purpose of this talk and presentation is specifically to address the existential threats and problems around the chip supply shortage and how India can take steps in solving that chip supply shortage and also getting ahead of semiconductor technologies by using quantum and AI in order to make up for the difference. So as Pradeep sir was mentioning before, this is a new opportunity: semiconductors, artificial intelligence, quantum computing. These are new opportunities to once again capture technical and global dominance in terms of the economic power that comes from being at the cutting edge of commercially useful and militarily useful technologies. If you look at what the Silicon Valley existence or industry did to the US became a superpower because it has a Silicon Valley, because it was able to spend billions of dollars in R&D and enable extremely cutting edge technologies that then unlock companies that unlock trillions of dollars in value today between Tesla, Apple, and so on. So how do we solve this, chip supply shortage? Well, first of all, what is a semiconductor chip? Just to recap, for the non-technical audience in the room, the semiconductor chip is a building block of a computer. You can think about it this way: the more semiconductors you have, or more building blocks you have, the more powerful and sophisticated a computer you can make. And the same applies for Lego blocks, right? So the first semiconductor transistor in particular was discovered by Bell in Bell Laboratories in 1947. Very quickly, soon after that, integrated circuit technologies came on board, and integrated circuit technologies were what enabled us to be able to make these more complex computing programs and patterns by making these smaller semiconductors and connecting them in ways that allowed us to compute information. And by computing information electronically, we were able to build machines and devices that made use of that electronic information. That is what a computer is, right? It computes information, converts it into something that's readable for a human to make decisions with and do various other things. So Jack Kilby of Texas Instruments was the gentleman who pioneered the integrated circuit. And then one key note to think about here is that semiconductors would not exist today if not for quantum mechanics. So none of the devices that we're running, our laptops, smartphones, GPS systems, defense systems, none of this, anything related to semiconductors would exist. And so quantum mechanics ended up playing a key role in the development of semiconductors and continue to. Quantum mechanics was actually very young and recently discovered as a field when semiconductors took off. So the completion of the Schrodinger equation in circa 1925 and onwards really marked the era of this new physics, and semiconductors were a pioneering technology from that new physics. And very quickly, over the span of less than 100 years, from 1925, semiconductors went from being these very prototypical, you could have like 5 or 6 on a integrated circuit, to having billions and billions and trillions in the palm of your hand. And so that means that translates today to a total industry size of $556 billion in sales as of 2021, where pretty much almost many of the technological applications that we can buy today, whether you're a consumer or you're in the government, requires semiconductors. Because again, semiconductors are the building block of compute, and compute means intelligence. The more access to intelligence you can embed into a physical product, the more dangerous and more useful that product becomes. So therefore, today's automobiles, today's household appliances like kitchen refrigerators, toasters, and so on, all require semiconductors because they're all running some kind of software program. And now another kind of, 2 key points to note here is this. Just last year, the automotive industry lost $210 billion just because of the semiconductor chip shortage. $210 billion is a significant decrease in market cap, as you can imagine, across these companies. In addition to that, semiconductor chips are in a geopolitically fragile state. So let's dive a little bit deeper. Why is there even a chip shortage in the first place? What led to this chip supply shortage? Well, first of all, there's a limited number of suppliers. So the leading suppliers like ASML, which supply instruments to TSMC, ASML make the photolithography machines that enable the fabrication of high-end semiconductors. Those machines are, first of all, far and few. They're very expensive. They take a long time to make, and they're very difficult to acquire. There's massive wait lists, and on top of that, as I mentioned, there's this geopolitical consideration, which is this. TSMC is a Taiwanese company. It is constantly at risk of being invaded or taken over by China. And if that happens, this is why I say this is an existential risk, the supply chain shortage of semiconductor chips. Because if that happens, TSMC is a leading supplier of chips to Tesla and as well as Apple and many other large tech companies used in the West, including Lockheed Martin, by the way, and some other manufacturers indirectly, right? So as a result, there is a fundamental issue there, which is that you have a number of problems. You have this geopolitical consideration, the supply chains, limited number of suppliers, and there's also long lead times in building these new fabrication facilities as well. So even if you wanted to build a new semiconductor capability, let's say for India, right? Historically, it would take anywhere from 7 to 10 years to build a semiconductor fabrication facility that can build a, let's say, chip that's at least as good as one that exists today, made by TSMC. So, just pulling that back a little bit, what that means is that at minimum, it should take us about 7 years to catch up to TSMC, where TSMC is today. right? That's basically the worst case scenario we're looking at. Now, it also costs billions of dollars in order to build these facilities. So it costs hundreds of millions of dollars to find a next generation semiconductor chip, and many, many more billions just to build the facilities around the fabrication for those chips. So where does artificial intelligence come in? Well, first of all, just to quickly recap artificial intelligence, in its simplest form, artificial intelligence is just software that is capable of using advanced mathematics to conduct pattern recognition and make inferences and decisions based on those patterns. That is the intelligence aspect. And so that's why we call it artificial. We're trying to program this intelligence, this ability to recognize patterns and go beyond just carrying out functions, but actually trying to understand relationships in data and doing something about it. Today, over the past decade, actually, artificial intelligence has exploded. So 10 years ago, roughly 10 years ago, was the first time that the world proved that artificial intelligence can actually be better than human written software for computer vision tasks. That was the first time that we had definitive proof that an AI can actually beat a regular human at something, at software design particularly. So that led to an explosion. Now AI is ubiquitous with top tech companies and even conventional technologies that you use today. So all the way from high frequency trading to Google search engine, to Tesla, to speech to text recognition, AI is found everywhere in actual mature existing products, as well as defense systems too. Modern defense systems use AI as well in various parts of their stack. If you look at what Lockheed, BAE Systems, and other aerospace defense providers have built and sold recently. So we are interested in using AI for semiconductor design. There is a pathway or a roadmap to essentially using artificial intelligence and quantum computing to essentially leapfrog the competition when it comes to semiconductor design. And again, I can't state enough or understate the importance of being able to at least have your own chip fabrication facilities and not relying on any other country at whatsoever, ideally, on building your own chips. Because these are the things that power the fundamental electronics of consumer products, as well as the defense systems that are relying on the chips. So for example, if China suddenly owns the chips that US missile guided systems are using, there's almost no point in building those missile guided systems. You will always be behind. Your tech will always be behind China's then as a result, because they're not going to sell you their best chips at that point. There's no incentive. They'll only sell you their slightly worse chips and so on. So there is a massive need to be able to make your own chips. And the way that I think we can do this, and the way that our business is actually trying to do this and solve this problem, is by building a digital twin for semiconductors. A digital twin is a representation or a simulation of a physical object. So in our case, it's the semiconductor, and we want to be able to represent it on a computer, represent the physics, the chemistry, everything that goes into the physical aspect of the semiconductor in order to be able to optimize it and model it in the simulation rather than doing it in real life. So the idea is to take a simulation first approach where instead of spending hundreds of millions or billions of dollars in R&D, physical R&D, trying out new semiconductor compositions, material structures, and so on, you should be able to one day simulate your semiconductor prototype and see how it's going to behave without physically needing to make it, and then using an AI to optimize those design parameters for you so that when it's time to actually invest those hundreds of millions of dollars and billions of dollars, you're investing in making the best possible chip possible rather than some almost a suboptimal version that a human scientist or group of human scientists might come up with. That is the thesis of why we should use AI for semiconductor design, is fundamentally because representing the physics and solving the equations that allow us to simulate these materials requires extremely powerful supercomputers today. So conventionally, if you wanted to simulate a semiconductor at the atomic level, you would use something like density functional theory. Density functional theory, as well as post-density functional theory and molecular dynamics, would all enable you to model what's happening at the atomic level between each of the different, let's say, electrons in your semiconductor lattice. You would be able to model the defects, the oxygen vacancy defects, the impurities, and so on in these semiconductors. This conventional software, however, takes a very long time to run. Often these simulations of just one configuration of a potential semiconductor might take a day or a day and a half to run. And that's just for one configuration. You might be 1,000 configurations away from a semiconductor that suddenly leapfrogs India, right, from the rest of the world in comparison. So it's all about how can we go and test all the possible different configurations in a systematic and intelligent way to develop these new advanced materials. And that's where AI can come in. Instead of having conventional software solving these equations that enable us to simulate the underlying physics of these materials, we want to be able to use artificial intelligence instead to solve those equations, and they would be able to solve it faster. This is something that we're proving out the viability today in our own company and with our own systems. So we see the future and potential of AI, and we see that it's actually enough and mature today. It's going to be useful today to give people an advantage. So that's very awesome. And just to kind of like tie up the point of why do these simulations take so long to run? Why are the mathematical formulas so difficult? They are difficult because in building these semiconductors, you have to be able to model the quantum phenomena. Modeling quantum phenomenon requires being able to solve quantum mechanical equations that describe your entire system. Those quantum mechanical equations are often very, very difficult, complex partial differential equations that require extremely difficult numerical methods to solve. So you have these very, very complex mathematical equations that take a long time, lots of computations, lots of complex computations to do. So imagine if instead of taking several days to run these simulations, we could run them in a matter of hours. And here's an example of how GenMat is doing something similar today with an existing class of semiconductors. This material that you're seeing here in this lab, in this SEM, is a titanium dioxide photocatalyst that is capable of converting sunlight into natural gas. Now, if you think about the implications of that, what that means is that if you could scale such a material and improve its photoconversion efficiency and solve the manufacturing problems associated with synthesizing such a photocatalyst, you would be able to generate independently of any other source your own natural gas, your own energy that could compete with natural extraction methods and purchasing the natural gas from other countries. So once again, this is an example of a material that could really revolutionize and change the game in terms of geopolitical power. So this simulation that you're looking at here, what we did was we wanted to ask ourselves, what happens if you deposit copper or platinum or copper plus platinum which results in a state-of-the-art photocatalyst today when you have copper, platinum, plus titanium dioxide combined together. We wanted to understand what is more likely to bind to the surface of the titanium dioxide nanomaterial. Is it copper or is it platinum? Now, traditionally, calculating this, let's say by hand, would be essentially impossible for a human to do. You have to compute this with a supercomputer because it requires solving many, many of these partial differential equations and linear algebra problems that I was touching on earlier. So in the end of the day, what you're looking at here is a simulation of a group of copper atoms that are on top of a titanium dioxide surface. And we were able to predict whether the copper is more likely to bind when there's an oxygen vacancy, so when you remove an oxygen, or whether it's more likely to leave the system or be repelled. And so we found that it is actually less likely and not favorable into binding to the surface, whereas with platinum, we found is favorable to binding to the surface. This allows us to essentially improve our manufacturing methods for this semiconductor device for photocatalysts, because now we know that we should be depositing platinum first, right? Because platinum, we learned, binds favorably to the surface. So why would you put copper, which doesn't bind favorably, right? There would be more energy required in putting it together. So these are the kinds of benefits that simulations offer us, because it would have taken us at least hundreds of thousands of dollars in several months to be able to validate these same exact different combinations that we simulated and went through. The same thinking and logic applies to the semiconductor industry today, where the semiconductors that are being built are at the several nanometer scale level. These materials that you're seeing here are these particles, these nanoparticles, are anywhere between 10 to 25 nanometers in scale. So the semiconductor industry today is already solving problems at this scale. The only problem is that there hasn't been much breakthrough in the technology used to simulate things at this scale. So we want to, reduce this time from several days, from 1 day, 1.5 days on average, to hours. And then for certain kinds of material systems, certain parts of the material, quantum computers will be able to cut that down even more into potentially seconds. So that's where the importance of quantum computing starts coming in. Now, there is an important caveat here. Often it's easy to think that quantum computers will replace regular computers entirely. But indeed, there is more likely to be a symbiotic relationship between regular computers and quantum computers. And that symbiotic relationship is because sometimes normal computers can do specific computations that are just naturally better suited for classical calculations than they are for quantum calculations. And sometimes quantum computers can do things much faster than a regular computer. I'll give a very funny example, right? So with RSA encryption, in roughly 10 to 15 years, 15 years being the more conservative estimate, we expect to have quantum computers that have enough qubits to break RSA encryption that exists today. And it would be able to decrypt RSA files within 2 seconds. Compare that to the billions and billions and billions of years it would take the most powerful supercomputer in existence today to crack a single RSA encryption. And so, however, what's really funny is that if a quantum computer, if you wanted to add 10 plus 10 or do simple addition, a quantum computer would do that operation slower than a classical computer. So for those simple addition operations, you're actually better off using a classical computer. It's cheaper. So there's this symbiotic relationship. And what we have to do as humans is understand how do we use quantum computers to our advantage. But before I get into that, very briefly, what is a quantum computer in the first place? So in order to understand what quantum computers are truly, first we have to understand the implications of quantum mechanics and how that understanding led to where we are today with building these new computers. So first of all, a quick primer in quantum mechanics. The double slit experiment is the most infamous experiment that essentially covers all of the strangeness in quantum phenomena, or at least a good proportion of it. And the idea is this. So we expect that when you have particles, such as a basketball, let's say, and if you had like a wall and you had two slits, we would expect that if we were to throw the basketball at the wall and we aimed it at one of the slits, it would go through that slit and it would land somewhere behind the screen and we could document it, right? And let's say that we instead built a machine that just started spit firing basketballs at this wall, and it goes through each of these slits. In the world that we live in today, these basketballs would create two distinct patterns, right? If you were just randomly shoot it across the wall, sometimes the basketball would deflect, sometimes it would bounce this way, sometimes it'll go through the slit. And eventually we should see a 50-50 split in terms of the basketball hitting the wall. It either went through this slit or this slit. Now, the strange thing about quantum mechanics is that if you were to shrink this basketball to the size of an electron, something really strange happens. When you shrink it to the size of an electron and you are no longer observing the system, meaning you are no longer making a measurement, you are no longer interacting with this system, and you allow the basketball to be fired, what ends up happening is this interference pattern ends up being observed at the screen. And that interference pattern implies that the basketball at some point in time became a wave-like version of itself, where it was neither here nor there, but really a wave that interfered with itself as it traveled through the slit in its wave form. So that's very strange. It's like seeing a physical object behave like a fluid when you're not looking at it. And when you are looking at it, it behaves like a just regular physical object again, instead of a fluid. So quantum mechanics is very interesting in the sense that we learn that the physical rules and intuition of how atomic principles, how atoms behave and subatomic particles behave are much more different than what we're used to day to day. And what you experience and what you see is this interference pattern. So quantum computers are computers that try to leverage these strange facts. They try to leverage interference patterns. If I start with an electron or a particle and it creates a wave, it behaves like a wave and interferes with itself, what can I do with that? Because now I can represent information in terms of these interference patterns. These interference patterns are probability distributions in the end of the day. So how can we create a form of computing using this stochastic modeling, these probability distributions created by quantum mechanics? And there's one final piece that quantum computers do. So remember, quantum computers leverage quantum mechanics. Rather than treating them as these side effects or things to engineer around, they actually use the quantum mechanical effects of nature to store, compute, and process information. So the other quantum mechanical phenomenon that beyond superposition, and a superposition, by the way, is what happens when you're not measuring the system. The particle will exist in a superposition of having gone through slit A and slit B. So between superpositions, interference patterns, and quantum entanglement, you can build a quantum computer. So quantum entanglement is another strange physical property where a state of an object cannot be described without describing the state of the other object, no matter how far apart they are in space. So that means that, again, take the basketball example. If we had two basketballs, one was black, let's say, let's say one was spinning towards you and the other one was spinning away from you. And you separated the basketballs from, let's say, 10 light years away. So one basketball is spinning towards you, the other basketball is spinning away from you. In a regular world, in the classical example, what we're used to, if I stop spinning this basketball that's spinning towards me, the other basketball 10 light years away should keep spinning. It shouldn't be affected whatsoever by what I'm doing to this basketball. But when you have entanglement, so if these two basketballs were quantumly entangled, if they were electrons whose spins are entangled, for example, what would happen is that if I stop spinning this basketball, so would this guy. If I flipped it the other way, this or the orientation, the direction of the spin of the other basketball would also flip too, no matter how far apart, and it would do this instantaneously. So technically the information, in order to decide which direction to flip, would travel faster than light. So it's these very weird and strange properties that quantum computers exploit. And this gives us an ability to perform computations and simulate quantum physical phenomenon in ways that regular computers simply can't, because it is so mathematically complex to describe these really exotic states of physics of matter in particular. And just one quick analogy to classical computers, just to really drive the point home that quantum computers are just computers, only they leverage quantum computing, is the following diagram here. So very quickly, these are, in a regular computing system, you start with a input bit string and you apply logical Boolean gates to it, right? Logical gates such as AND gates, NAND gates, NOR gates, XOR gates, and so on. In quantum computing, you also have, instead of bits, you have qubits. And instead of logical Boolean gates, you have quantum gates that you apply. And some examples of quantum gates are the poly X, Y, and Z operators. The Hadamard gate, for example, is a true quantum gate in the sense that it actually applies, it actually puts a qubit into superposition of two different states. A physical regular classical bit can never exist in a superposition between two different states, right? It never creates this interference pattern. So another example is this controlled Z gate. So quantum computers are a network of these really interesting unitary operations, right? This is the mathematical matrix that represents what that gate looks like. And what you get at the end of it is a powerful computation that can capture truly quantum physical phenomena. So how can we use this knowledge? How can we use quantum computers for semiconductor design? Well, first of all, quantum computers use quantum mechanics to represent and store quantum information. Regular computers use classical mechanics to represent, store, and compute classical information. And so what does that mean? Well, the world that we experience day to day at the microscopic scale, being billions and billions of atoms large, and the objects that we're interacting with, the mouse pad, the keyboard, the laptop in front of us, our glasses, these are all made of billions of atoms. So they behave based on classical physics because these are macroscopic objects. So the world that we compute information in, the way that we see it, is classical information. We measure the world classically. However, we know that if you zoom in to any physical object, those objects are made of atoms, and atoms follow quantum mechanical physics instead of classical physics. And so these quantum mechanical rules, the world of the small, they have intuition that are alien to us. It is not intuition that mankind necessarily evolved for survival, right? We are used to the world as it is today with classical physics, when you have billions of atoms, but we have very, very poor intuition for how the world of the small behaves. So quantum computers, however, allow us to compute this information. The way that the world of the small behaves, the information, the complex states they can be in, the ways they can interact, keeping track of all these rules, keeping track of all these states is very, very mathematically intensive and therefore compute intensive, and therefore is often very hard, if not impossible, for regular computers and regular algorithms to be able to model, because quantum physics phenomenon is just so complex. And so therefore, it makes sense to use a quantum mechanical system like a quantum computer to truly simulate another quantum mechanical system like the quantum mechanical systems that make up a semiconductor. So that's the fundamental principle, is that, okay, given that quantum mechanics plays such a fundamental role in semiconductor design, and given that quantum mechanical rules are very hard to simulate and require supercomputers or are just downright impossible to simulate, then why don't we use quantum computers that are also naturally exploiting quantum phenomenon? So that's the kind of thinking behind the use of quantum computers. And so, on top of that, not only can we then use quantum computers to properly simulate the physics and chemistry of what's happening with semiconductors at the nanometer scale, we can then train an artificial intelligence to optimize the semiconductor based on the simulation results. Right now, a human would have to interpret the results of the simulation to figure out whether they should swap in a new element, whether they should use germanium, or whether they should input like 10 oxygen vacancy defects on the surface, whether they should remove oxygen vacancy defects, and so on and so forth. What dopants, what impurities should we put in? All of these things an AI can start deciding on once it can physically model it better. And that's where the quantum computer comes in. So you have this symbiotic relationship where the quantum computer models the physics and the AI figures out what to do with it. And to the right here is Sundar Pichai, CEO of Google, and he is standing next to the Sycamore chip, which is the world's most powerful quantum computing device ever built till date. The Sycamore chip is a 54 qubit chip, and it uses superconducting hardware and superconducting wires in order to perform very complex quantum calculations that till date, the best supercomputers would take anywhere from 2 to 3 days to do what it takes this chip seconds to compute. So it's a really powerful supercomputer. And the way that it works is that it uses liquid helium to cool down through this cryogenic system, cool down the temperature to the point that it's just a few Kelvin to a few millikelvin above absolute zero. And at that point, you have the superconducting phase that you tap into, and then you can give it commands to perform quantum computations. So now, what can India do about the chip supply shortage? And what can India do knowing what it knows today, what the world knows today with regards to artificial intelligence and quantum computers and the impact potential that these technologies have? First of all, India can continue to invest and invest more in quantum computing, artificial intelligence, advanced manufacturing, and materials engineering technologies. Fundamentally, there is an opportunity to really become a superpower by dominating in these different technology fields, because the entire physical world will end up being completely designed and engineered by quantum computing and artificial intelligence and advanced manufacturing systems. and materials. At least the physical aspect of it will. That will enable all these other commercial technologies that we use today, like smartphones and so on. So the second thing that they can do is build relevant global partnerships with private and government institutions who are aligned with democratic principles. One thing that's really amazing about India is that it's a very young democracy. It's a very, let's say, some people might say it's a noisy democracy. However, that really is a good thing. It means that there's a lot of potential, a lot of new thought and optionality for the civilization and the culture to take right now. So it's not like it's stuck and rigid in some school of thought. So meaning it's not too late to invest in these technologies and partner with people and actually get things done. So the third thing is take a simulation first approach. This is a really good option, particularly it's really good option for anyone, but particularly incumbents, basically anyone who's competing or is trying to rise to the top will have an advantage by using a simulation first approach, because they will end up saving potentially billions of dollars and many, many years of R&D if they can design extremely hyper-realistic simulation technologies in combination with AIs to drive the decisions for the materials simulations. So by taking a simulation first approach, that will allow India to be able to essentially design the next generation of semiconductors, as well as the instruments required to build those semiconductors, because that equally is just as challenging. The manufacturing, the facilities behind that also requires innovation in the photolithography, for example. And those are also very difficult quantum physics-based material science and control problems. So the fourth one is start small and end big. It's not realistic to expect, let's say, a country like India or even the US for that matter, to spend like, let's say, enough money, let's say $50 billion in order to catch up to China over the next few years. I think that's impossible with the current strategies that both countries and their leaders are putting. So the US, for example, has committed $20 billion to Samsung. They committed, I think, a total of $53 billion to semiconductors in general, but that's only half of how much TSMC has committed to semiconductors over the next 5 years. And so that's just one semiconductor company, right? Spending more money than an entire American country. So it's going to be highly unrealistic to not take a simulation first approach in trying to catch up with the semiconductor industry and make our own and beat existing suppliers and so on. The last part, so that means that we should take existing fabrication tech that is cheap and figure out how can we optimize that using our AI and quantum computing platforms in order to at least get started and build a baseline capability of being able to do semiconductor manufacturing and optimizing that. So can you do it? Can we do it algorithmically, right, for easier semiconductors? And then the last thing is, I think India needs a 10-year roadmap. It needs to be able to clearly plan ahead of time where AI is today, where it's going tomorrow, the next 10 years. And the same thing applies for quantum computing. It needs to be able to clearly understand where quantum computing will be in 3, 4, 5 years from now, and 10 years from now, and how they should be integrated into the overall manufacturing supply chain for semiconductors. And with that, I conclude my talk. Thank you.
Thank you very much, Deep, for a very insightful talk on a very pressing issue of quantum computing, artificial intelligence, and its use for self-reliance in the semiconductor manufacturing space, especially in India.